AI has its own unique trajectory of a roller coaster ride where every 10, 15 years people are like, we're doing it, we've solved it. And then it kind of falls down in the hype.
Last week we talked about depth,
Yeah.
and if anything, we've gone deeper into depths of product management before that and team building, and we're getting some great responses from people. I'm seeing the compound effects of what it means to really start something. This is going to be our 6th episode. Thanks to our viewers and people who have been really active and giving us feedback as well. And you and I were talking about what does it mean to get deeper into understanding AI. So today is that episode where we get a little deeper into history of AI, which is about 50 years of machine intelligence and machine learning, and now artificial intelligence. In many ways, it takes that long to really build something of meaning and value and pervasiveness. You and I were talking about how it took 50 years from the beginning of the discovery of the double helix structure for DNA, like late 50s, early 60s. A ton of physicists and biologists and biochemists coming together and basically saying this is how things are coded for life. And then it took 50 years before mRNA, which is a cousin of DNA, really solved something as big as the COVID vaccine problem, the fact that we could save so many lives. Similarly, it took 50 years from the beginning of the invention of, let's say, screens, TV screens, to where we are with touchscreens in mobile and becoming so pervasive that these computers are in our pockets. And of course, microprocessors from the early 50s of vacuum tubes and ENIAC computer, which was massively large computers, to where these things have come in those 50 years to really being computers in the hands of 8 billion people and counting. So it takes that long to really build something of value. What do you think?
Yeah, it's definitely interesting to draw those parallels, although I guess AI has its own unique trajectory of a roller coaster ride where every 10, 15 years people are like, we're doing it, we've solved it. And then it kind of falls down and the hype crashes, and then it takes that long to recover from it and then build another level of excitement and new innovations.
But I do believe, and to be fair to AI, I think this happened in computing as well.
Yeah.
We talked about paperless office for the longest time. For the longest time, we talked about paperless office. And there's still so much paper, even after 30 years. DocuSign is only a new concept. Only in the last 5, 7, 8 years I've been talking about digital signatures for mortgage and all these other things. I think there's so many other examples I can provide for how computing was fleeting in many ways. And then we said, it's going to get rid of it. Like in my past business at Nutanix, we kept talking about virtual desktops. This is the year of the virtual desktop. This is the year of the virtual desktop. And I think there is so much push and pull for any such architectural change. It takes that long to.
Yeah.
So I think computing itself has had to go through so much to prove that I feel like it's only fair to talk about those things as opposed to just AI alone.
Yeah.
But let's go back to the 50s and the 60s. Let's call it the era 1.
Yeah.
The early years of interpolation and the just struggles with convergence. I want you to talk to the people about just even defining interpolation and defining converging algorithms, and maybe we start with those years of mathematics and go from there.
Yeah. So actually, as far as AI is concerned, there's been an interesting mix of different disciplines. Mm-hmm. So in 50s, it was actually coming more from the biology side, where people were trying to understand brain. And once they started understanding the structures, it started looking like there was a network of these things which had mathematical properties. And it was less about that can we build a computer-like brain, to can we explain the brain as a computer, was the motivation behind the research in 50s, and that led to modeling the human or biological neural network as a mathematical neural network. And what became apparent is that, to a rough degree of approximation, what's happening in a single neuron, you could represent it as like weighted sum of inputs followed by a nonlinear function that's kind of a thresholding function. Or
so you said a lot of things actually in those last two sentences. We got to slow down for the people as well, including for me actually. Weighted sum of inputs.
Yeah.
Explain the physical nature of this observation. Like, what does it mean to say weighted sum of inputs? Like, and I'm sure we see this in life at large. So let's start with that, and then we'll get to the next few words you said.
Okay, so I think I'm gonna butcher the biology here a little bit, but essentially what happens is that, so neurons are these cellular structures in brain, and they're connected through synapses. And so the base level neurons are getting triggered by the sensory input coming in, these electrical potential, right? So this electrical potential will cause ions to rush at one end, and then some electrical potential to travel from one cell to the other, and then another set of ions to go. And the thickness of this connection determines how much of the excitation here results in excitation over there. So there's this weight in the middle that essentially is modulating how much electrical excitation from one neuron travels to the other. And one neuron may have multiple connections. It could be hundreds or thousands of connections actually. So all these excitations are now getting added up, and then...
And do these neurons have defined roles in the brain? And when you say the thickness of these connections, do they have any kind of a meaning between these neurons?
So this is something that people are still trying to understand. At an individual level, a neuron doesn't have any meaning. But the structure of neurons in different parts of brain are doing different things. But they're also retrainable, and you can reclaim some space in brain that used to do one thing and retrain it to do something completely different. So it does feel like these are sort of basic Lego blocks that can be assembled to do anything. So, for example, there have been interesting experiments where, for blind people put sensors on tongue, which projects image. So for every pixel, there's a pressure actuator that applies pressure on different parts of the tongue. And people were able to see through their tongue because the brain is that programmable.
Fascinating. So we were on the weighted sum of inputs.
Yeah.
So you start with biology connected to the math.
Yeah. So now we come to the mathematical version of the neuron, right? So each neuron is taking inputs from, let's say, n different neurons, and then the thickness of the connection, the strength of the connection, varies based on what we have learned, what our brain is learning. So that's where we say brain is plastic, because these connections can change. So let's simplify things, and let's say that 0 is a inactivated state and 1 is an activated state, right? So each of these neurons are firing zeros or ones, and then through the strength of these connections, there is, let's say, the strength of first connection is W0, and the next one is W1, and next connection is W2, and so on and so forth. So if the first input neuron fires, then I get excitation proportionate to W0. And then if the next neuron fires, I get excitation proportionate to W1, and so on and so forth. And then all these things get added together. So that's the total amount of input excitation happening in neuron. And then there is sort of a nonlinear function there. So this sum goes through a sigmoid-like function. So if it crosses a threshold, then the neuron will fire on the output side. And if it doesn't cross that threshold, then it won't fire on the output side. And it's not completely 0-1. There's a level of continuity in the middle. And then this firing will then go feed a bunch of neurons at the next level. Right? So it's just, you take the weighted sum of your inputs, which are zeros and ones, and then you run it through a sigmoid-like function, and that gives you the output of this neuron that feeds into the next layer.
Got it. And at some level, how many layers of these neurons do we have in our brains, and how many neurons do we have in our brain?
So I think I've read the estimate to be about 10 to the 15. Number of layers, I couldn't say.
Got it. So we're still probably trying to understand this. I've, for some reason, also remembered the number 100 billion neurons. Is that 10 to the 15 or?
No, 100 billion would be 10 to 11.
11? I see. Wow. So it's bigger, deeper than that. Yeah.
Yeah.
Fascinating. So what was going on? Again, going in the 50s and the 60s, we talking about interpolation and convergence.
Yeah. So that led to, on the mathematical side, people modeling these artificial neural networks. So now imagine you have just one layer of neural networks. So you have a bunch of inputs coming, and these different neurons are doing weighted sums of inputs. Each neuron has different set of weights, and then comes a set of outputs that go through a nonlinear function. Now, up to the multiple weighted sum, you could essentially think of it as matrix multiplication, right? Because you have a set of inputs coming, which is like an input vector, and then you have columns of weights, each neuron, and you put them together, it kind of looks like matrix, and then you do the matrix multiplication, and out comes the output activation from these neurons, and then they all go through a very similar nonlinear function.
Is it a matrix or just a vector right now?
So the input is a vector, and the output is a vector. The weighted sum that's happening in the middle across multiple neurons can be modeled as a matrix. So you can collapse all these neurons into one, and then imagine the entire layer being a matrix.
Got it. So for people who are probably a little bit new to mathematics, explain the difference in a vector and a matrix. A vector is basically a special representation of a matrix, which is one dimension, n times 1, or 1 times n, right?
Yeah.
Okay, so what was the struggle with convergence? First of all, what is convergence here and so on?
Yeah. So now the first idea that is interesting is that essentially these artificial neural networks are programmable mathematical functions, right? So you can change these weights, and you can put these, for any given set of weights, you give these inputs and certain outputs come out. So this whole machinery can be thought of as a function.
As a math function.
As a math function. And these weights are the parameters of this function, and you can change them and you can get different outputs.
So you said three things here. There's inputs, there's parameters, and there's outputs.
Yeah.
So for those who've actually done programming, they'll probably understand parameters. What about for those who don't know the difference between inputs and parameters? Maybe explain a little bit on that.
Yeah. So parameter is kind of like
behavior?
Kind of like a knob, right? So think of it as, let's say you have a light switch and you turn it on or off. So the switch, whether it's in on position or off position, is the input, and the light you're getting from the light bulb is the output. But imagine if I have a knob in the middle that I can turn
for intensity
and so the setting of that knob is like parameter.
Got it.
And so in this neural network, imagine having billions of these knobs that you can turn, and as a result it can model different things.
Great. At some point we'll get into a little deeper into the word parameter. But for now, let's just say that these are knobs. Keep going, I think.
So now the first idea is that this is a very powerful class of functions in the sense that only by turning these knobs, I can model many, many things. Just like our brain, can learn many different things. It can learn to classify images, it can learn to write text, it can learn to produce music, or solve complex math problems or planning problems. This network is also a function that can generate all kinds of output, and all you have to do is just find the right setting for these knobs. Now obviously that's much harder, but there's the idea of training a neural net, that how do I find the right setting for these knobs so that it does what I want it to do. And that essentially became a math problem. And what started happening in 1950s where people were building these neural networks called perceptrons, which was essentially layers of artificial neural network with these weights. And the goal was, for a simple task, can we train these things to do what we want it to do,
and to come up with a predictable outcome?
Yeah.
Okay.
Yeah.
Okay.
So let's say, for example, you have pixels of an image, and you want to see whether it represents the digit 1 or not. And so the output would be 0 or 1. The input would be, let's say you have 8 cross 8, 64 pixels, so 64 0 1 inputs, and the output is a single digit. And in between, you want to plug in a neural network where you can adjust the knobs so that only when it looks like 1 does it produce the output 1.
Got it.
And so,
and where was this problem of, I can't get the weights to really work, and therefore the problem of divergence?
Yeah. So initially, people were trying simple classification tasks where you would provide an input and output would be, let's say, 0 or 1. And as long as you could imagine these things being what's called linearly separable. What that means is that imagine the inputs you're giving are points in the 3D space, and the points over here represent class 0 and the points over here represent class 1, like something that we want, something that we don't want. As long as I can imagine a plane in between that cleanly separates this side from this side, there was a direct algorithm for computing the weights. And there was basically an iterative method. As long as you had the training data that says that these points in 3D space belong to class 0, these points belong to class 1, and there was a separable plane, we could find the right weights for the neural net, which essentially corresponded to the plane in the middle. And then we could build something that would work.
Got it. But it was a struggle, which is when we get to the 80s and the 90s, actually.
Yeah.
Where, you talked about these new ideas called gradient descent and, simulated annealing and back propagation. So what are these terms? I mean, I use 3 big terms right now. Simulated annealing, gradient descent, stochastic gradient descent, and back propagation.
Yeah. So now, if you have just single layer of neurons, then you're required to do this linearly separable thing. And that actually falls down pretty quickly. So imagine the function XOR, where 0, 0 will produce 0, 1, 1 will produce 0, but 0, 1 and 1, 0 over here will produce 1. So there's no line that you can draw that will separate the ones from zeros. You kind of have to draw one line, like one plane here and one plane here, and say this side and this side both are 1, and the middle area is 0. So this couldn't be done with a single layer. Now, of course, you could solve it with multi-layer, but there was no known algorithm that will converge that nicely to give you the weights. And this result had a chilling effect on all the excitement around neural nets.
The fact that you couldn't XOR.
Yeah, you couldn't train XOR with a single layer. And multi-layer, even though you could, there was no well-known training algorithm that will kind of converge and give you the right result. In retrospect, it kind of seems silly that sort stopped science, but I think people got very excited about programming and logical modeling of problems as opposed to trying to do these things through fuzzy weights, and that's where the momentum went. And then it took another decade before people came back. So now...
I could see why XOR became an exciting function, because even in real life, people are trying to find differences, not just commonalities.
Yeah.
In many ways, XOR is a physical thinking of, are they different, are they the same? And when they're different, they want to actually light a bulb, which I think is a very powerful function. So there's something to be said about if you needed two planes to actually talk about this, there's something more to it, So what happened with, what is the idea of backpropagation at some level?
Yeah. So the idea of backpropagation, I think in general, it applies to any kind of optimization. But neural nets in general, the training of neural net, you can think of it as an optimization. So I have these parameters. I have my training data, which is inputs and outputs. And I have an error function. So this error function essentially says that I was expecting this output, but my neural network or my tunable parameter math function is producing this output, and the delta is the error. And when you aggregate all the error that you're seeing, then there's an aggregate error function, and that's what we are trying to optimize for. Minimize the error as much as possible. So a simple example is linear regression, where we're saying that the line is predicting the value of y given x, but in real life the points are all over, they're not following a straight line.
People look at standard deviation and things like that.
So my error is essentially the square of distance from the predicted value to the actual value, and if I sum up these squares of distances across all my training data, that's my error function, right? So now I have a function that I'm trying to find the minima of given the parameters that I have, and so I can simply just take the derivative and try to follow the derivative and get to the local or global minima of that function where these parameters are such that my error is minimized.
So say that again slowly, because you introduced the notion of a derivative, which is saying that if I change these things in the parameters, then this is how the error function changes. And you basically talk about how these things need to be, the knobs need to be tuned for the error function to be minimized. So what's this idea of forward propagation and back propagation?
So let's say that I have multiple layers of neurons, and each neuron comes with a set of weights. And if I make a small change to the weight here, it's going to have some impact on the output it's producing. And that means it's going to have some impact on the difference between the expected output and real output. So it's going to have impact on the error. And not just on one training example, but on all the training examples I have. And let's say that I'm trying to reduce the square of errors. So it's going to have some impact on the sum of square of errors. Now, what I want to do is compute what's the rate of change. When I change this weight a little bit, what's the rate of change on the sum of errors? And then I want to adjust this weight in a way that it reduces overall error. Now, I can't go too far, because that rate of change also changes. But locally, assuming that I've used all the smooth functions, if I make a small change here in the direction that favors the gradient, the error should go down.
You used the word gradient for the first time.
So gradient basically means the rate of change of the error function with respect to the rate of change of a particular weight parameter. So that's the gradient or slope or derivative, right? And so I want to compute that derivative, and then in the direction of the slope or gradient, I want to make a small change here. And so that's called gradient descent. And I'm doing this for all the parameters in my network. And so that would be the gradient descent method.
I think maybe this is a good time to slow down and maybe get into the visual thinking about gradients. In fact, Stephen Wolfram talks about the idea of water and mountains, and valleys. So maybe talk about water and valleys and things like that. That might be able to make this concept a little simpler.
Yeah. So in a way, you can draw an analogy between let's say that we are in a valley of some sort, right? And
it's a very hilly area, it's mountainous.
Yeah.
And we're trying to find the deepest lake or something, yeah?
Yeah, yeah. And so you can think of the contour of Earth where they're as a mathematical function. Right? So there is input is the x and y coordinate, and output is the height in the mountain or the valley where we are, right? So that's the math function. And if we wanted to find the deepest point, we could just pour water at any point and water will run to the deepest point. At least that's kind of obviously locally the deepest point. It will run there. And the way it will run there is it will find the steepest slope that it can, the direction in which this slope is the steepest, and the water will just run that way. And eventually it will reach some place which we can call sort of local minima. Or
so that's a local lake that
Yeah,
actually
that's a local-
forms, right?
Yeah.
Yeah, please go ahead.
So now finding the direction of the steepest slope is essentially the act of taking the gradient, or like differentiating this math function which is giving you height given x and y with respect to x and y. And basically those, when you differentiate this function with respect to x and with respect to y and then treat them as vector, the direction of that vector gives you the direction of the steepest descent.
And that's what scientists are trying to figure out.
That's
what's the fastest way to get to
Yeah.
the global minima of this error function.
Yeah,
Which
yeah.
because our whole goal is to minimize the error.
Yeah.
So we're trying to find the deepest place where the water will come and rest.
Yeah.
So simulated annealing, like there was something about shaking up the water. So say more on that. You know.
So this is kind of a technique that's being used in broadly optimization or in operations research kind of thing. Where,
And converging the algorithm as fast as possible.
Yeah. So now in real life, you don't just have like one convex plane where like everything just goes down to the lowest point. You have many hills,
Peaks and valleys, yeah.
Peaks and valleys, and in that case, the water can get stuck in a local lake, whereas there is a much deeper lake over here. So how do you find the deepest point on, let's say, Earth or in a given region, when all you can see is the slope locally? Right? So one way to do this is that you proceed towards the local minima, or sort of you follow the gradient till you get to a place where the gradient is, there's no slope and it's flat, and in its surrounding neighborhood it's guaranteed to be the lowest point. But you may have to jump over a hill to get to another deeper place, right? And so the idea of simulated annealing, which is taken from metallurgy, is that when you get there and you're stuck there, now you don't know where to go, you kind of take a random jump from there.
So you shake up the whole thing.
Yeah, you shake up the whole thing and it kind of jumps out of there and lands somewhere else, and then you try that again. And hopefully one of these times that you try, you end up in a place where if you follow the slope, you get to the global minima.
It's fascinating how even in our own lives, we talk about fooled by randomness.
Yeah.
The idea that you actually need to create this entropy for things to emerge, and obviously we've read Nicholas Taleb's book on randomness as well. Looks like we're trying to apply that level of entropy to get to another global minima and so on.
Yeah. So people are trying to find all these techniques so that things don't get stuck in local minima, and simulated annealing is one of them, where you kind of initially when you shake up things, you shake up by quite a lot. So essentially you're raising the temperature to very high, so the random jumps are far places. But as time progresses, the hope is that you kind of, in many tries, you have found a place where things are a little bit deeper. So now you don't want to jump that far from there. and so you gradually decrease the temperature, which is the part of annealing.
Interesting how, like, if I were to visualize this, I'm like, if there is a lake that's here and the hills are approachable, then the randomness, it can actually climb that. But if it's a really deep lake and the peaks are way higher, even if you create randomness, it'll eventually come and settle down right then and there.
Yeah.
So there's something about physics here too, which comes into play as well.
Yeah.
So backpropagation was about going outer layers in. Why?
Yeah. So now we're talking about training neural nets that are potentially several layers deep, right? So how do I compute the gradient of a weight parameter here, which is several layers behind the actual output, right? So if you remember the chain rule in differentiation, you kind of, if there's a function of a function of a function, you take the derivative of the first function, multiply it with the derivative of the second function, multiply the derivative of the next function, and so on and so forth. So these layers are essentially simple functions composed of other functions which are sort of outer layers. So you can think of a 3-layer deep neural network as like a function of a function of a function, right? And the final function is the one that's giving you output. So now if you want to take the derivative with respect to the input to the function that's 3 layers inner, you need to multiply the derivative of the first, second, and the third function. So this is the chain rule that applies in taking partial derivative of a given parameter with respect to the error function. So you compute the gradients of the parameters at the first layer with respect to the error, and then those get multiplied to the gradients of the second layer, and those get multiplied to the gradients of the third layer, and so on and so forth. We're going from out to in. So now, as I'm trying to find the direction of steepest descent, I want to compute the gradient of all the parameters in my neural net. And imagine this being like billions of parameters now. Right? So it's actually substantial amount of compute to look at these functions, look at the current value of these functions. Because remember, like for example, if you're taking derivative of x squared, it's 2x. That means that the slope is dependent on the value of x. So whatever the inputs you have provided and whatever the activations are there, it's the gradient is a function of those activations. It's not a static thing. So for every input, the gradient is different. So for every input, now you're computing these billions of partial derivatives. So what's an efficient way of doing that, right? So obviously you want to reuse the gradients that you have computed for outer layers as you go to the inner layers. And you reuse it many times because it's like a reconversion network in some sense, right? Like you start from here and your outputs go fan into multiple neurons, and their outputs fan in again to one neuron. So if you did it naively, you would have an exponential blow up because the number of paths here along which you want to multiply the gradients and add up is exponential.
So is there anything that this community of computer science or scientists or AI researchers learned from operations research, for example, where we were trying to do, I mean, there were networks in OR as well. And if anything, we went through these classic problems of traveling salesmen and things like max flow, min cost. And I remember this is mid-90s when we were doing our undergrad, we were talking about actually backpropagation, and the idea of really starting with the end and then going backwards. Is it the idea of working backwards? Is there anything that AI researchers took away from OR as well?
Yeah, definitely. There's a lot of parallels between OR and machine learning in general, because the focus in both places is optimizing through nonlinear functions that are not necessarily convex. So if you're dealing with convex functions, then it's relatively simple. They just keep following the gradient, you will come in place. But if you're going through functions that are non-convex, then both OR and machine learning struggled with how to find the global minima or somewhere close enough to global minima. And so this idea...
I'm not going to go into rat hole of defining for people what convex, non-convex means, but maybe at the highest level, you could say something about the physicality of convex and why it matters.
Yeah, so imagine you have like a bowl, right? So convex shapes like something like this, where you can put a drop of water anywhere and it'll get to the center where it's the deepest, right? But you can imagine lots of shapes that are not like that, where like there are hills and valleys and stuff.
And we talked about the XOR function early on as well, saying, look, it's not. Right? Because if I draw one line, it could come multiple points. Now I don't have a function, because for one input, you could have two outputs. And that basically is the same hyperplane problem as well, that I don't have a clean hyperplane that separates this from that. Is that a good way of putting it?
Yeah. Like you can model XOR as a simplest non-convex
and
function.
we're trying to find convex because... Why does convex matter?
So if the function is convex, then finding the global minima is easy. You can just kind of follow the slope and you get to the lowest point. When the function is non-convex,
it's jagged.
It's jagged, and you can't see the whole thing. Like you don't have the luxury of I'll look here, and here, everywhere, and find the lowest point, because we're dealing with billions of dimensions. It's not just simple 2D function. So,
and it's also not a function by the classic definition of function, right? Because for one input, you could have two outputs. Is that another way of thinking about it?
I mean, that you can just say that there's a vector function. So the output is a vector. So there's multiple outputs.
Got it. So going back to this, obviously standing on the shoulders of the giants of OR, and we were looking at 80s and 90s where some big things changed, and there was something about stochastic gradient descent. So we were talking about gradient descent. We introduced it probably at a high enough level for everybody to understand. What was the struggle for which this aha moment of sampling really came into being?
So machine learning has this interesting, maybe everything in life has, that most ideas are like hundreds of years old. It's just the engineering part that is the unlock. Like there are lots of these ideas that like you can trace all the way back to mathematicians like Cauchy and stuff, and they were known, but like how do you take this idea and apply it to this complex problem and get meaningful results is where the unlock happens. So the idea of stochastic gradient descent is another one of these ideas. How do you avoid getting trapped in the local minima? By adding a lot of randomness. So one style of adding randomness is that I'm not going to compute error across all of my training data. Let's say I have 1 million images that I'm training on, and let's say I have 1 billion parameters. I'm not going to compute gradient of million times billion, and because that's very prohibitive. And when I do that, anyways, I get stuck in local minima. So what if every time I have to do this, I take a random sample of 100 images? Now, statistically, if the nature of the problem is same, the gradients should follow the same distribution as the whole, but there is substantial amount of randomness in it, which will allow me to escape local minimas. And over time, as in general, I'm generally trying to go to lower and lower values of error. The idea is that if I keep doing this enough times, overall the global error will come down and it has the added advantage that my amount of compute goes down, because instead of looking at all my million training examples for every step, I'm just looking at a random sample of 100. So that's the idea of stochastic gradient descent. And I think people like Jeff Hinton did an amazing job of taking these old ideas, applying them along with backpropagation to show meaningful results in modeling
converging the algorithm. Got it. Interesting. So we talked about two eras right now, the 50s and the 60s, and lack of finding easy ways to converge things, to the 80s and the 90s, where we use physical things like annealing, which is raise the temperature, increase the randomness, or even stochastic backpropagation, increase the randomness and see if the water really comes out and settles in a better valley than the previous one. So now we are in era 3.
Yeah.
I'll take the 2000s. So we went through 60s, 70s, 80s, 90s. Now talking about 2000s, GPUs and matrix, obviously, in some sense, computer visualization, just vision problem, visualization problem, graphics problems actually come in. Say more about that decade, like what was going on, and in many ways the dichotomy emerges in the computer architecture industry between Intel and RISC, or ARM, one could say, and NVIDIA.
Yeah.
So there's a whole path that CPUs are taking.
Yeah.
There's a whole path that GPUs are taking.
Yeah.
And in some ways, the assembly line for CPUs was getting more and more complex.
Yeah.
Because the instruction set was complex. And here there's this other path which is emerging, which is quite the antithesis.
Yeah.
Saying simple instructions, data structures are a matrix, and so on. So try to explain to our audiences to what was going on in the computer architecture industry between complex instruction set and reduced instruction set, and why it matters today. So we need to really paint the picture of these two different computer architectures emerging, and why NVIDIA is actually looking so glum and happy right now.
Yeah. So I guess there were kind of 3 different classes of microprocessors that were evolving. So the initial microprocessors were all like, you have an ALU and you have a few instructions to load and store and do some math with it, and some input output, and that's pretty much all you get, right? And as our software started getting more and more complex, people wanted to do more with the hardware. Now, there's 2 ways of doing more with the hardware. One is that you make your instruction set more complex, which means that you have dedicated functionality on hardware that's designed for common tasks that arise in programming.
And memory was still scalar.
Yeah.
So we kept data simple, or data structure simple, but the code became more and more complex.
Yeah. So people were trying to do like multiply and addition in a single instruction. They were trying to do like predicated logic, that if this condition is true, then only add this to this. So you're kind of combining 2-3 instructions into one instruction, and you're throwing more transistors at the problem and getting the speed up that way. The other way was more parallelism, right? So you just build more and more CPUs on the same silicon, and so you're able to give parallel instructions and say like one thread is doing this, another thread is doing this, another thread is doing this.
Provided they were parallelizable.
Provided they were parallelizable.
Which in itself is a hard problem.
Yeah. So the CISC people, the complex instruction people, said that, like if I know the things that need to be done in advance, I can do the best job of parallelizing it using transistors. You don't try to do the parallelization in software. Just we will do deeper and deeper pipelines, and we'll do better branch prediction and things like that. And so that way the CPUs kept getting more and more powerful, and Intel followed that path of throwing more and more transistors per core to give it faster instructions, more complex instructions.
So in some sense, it started making monolithic processors.
Yeah. Intel also had multiple cores, but each core was much more beefier.
Yeah, at a micro level. Yeah.
And on the RISC side, people said just build very simple microprocessors and do more of them because they take fewer transistors. So do more of them, and then at software level we can drive more parallelism, and that will be better.
And then there was something about memory as a matrix that became fundamental to this latter side. What about it, at least when you think of the obviousness of this, like at some level there's logic and there's memory or data. Did these guys start taking a 2-dimensional approach to data, or maybe even more, that basically made representing data as a matrix as a fundamental building block of this versus that? Did that also change the equation?
Yeah, so this is where we come into the graphics side, right? And the SIMD, simple instruction, multiple data side, right? So now video games are getting popular and people building dedicated hardware to make rendering of generated 3D worlds easier. And what does that mean? You're doing ray tracing. What does ray tracing mean? You get a light source here, and then it's traveling in all different directions, and then it hits a surface, and based on the texture and the color, some light gets absorbed, some light gets bounced off, and then you follow that light again to where it goes, and so on and so forth. Right? So now when you're computing the result of projecting a lot of light rays going through 3D geometry, you need to do a lot of matrix multiplications. Because matrix multiplication essentially gives you like a way to rotate things and scale things. So these things were called shaders, which will essentially do the tracing of light and compute the value of pixel, like multiple pixels, based on how the light lands in that particular.
And was it also about next scene from the previous scene? Was it similar to next token that we see from LLMs, or was there enough sort of incrementalism in gaming that also needed special hardware, special matrix thinking, or what was it about motion that made this problem even more complex?
So I think that probably will get deeper into a rat hole that we can preserve for another time. But essentially, the crux of it is that as we were tracing the rays from light source all the way to camera through a bunch of reflections, we needed to do a lot of matrix multiplications and additions. And when you have that, there's a certain amount of predictability in terms of what compute you want to do and where the data needs to be read and written into memory. And you can take advantage of that. So this is where the idea of SIMD applies, which is single instruction, multiple data. So you're issuing one command to a whole bunch of microprocessors, same command, but they just have different pieces of data, different parts of the matrix or different parts of the pixel, but doing the same operation, which is multiply by this and add by that, right? And if you look at even a simple microprocessor, the amount of circuitry that's needed just to do multiplication and addition is tiny. It's the amount of machinery that tells which multiplication, which addition to do, like which thing to fetch from memory and where to store it, that and when to do it. That's the stuff that takes a lot of transistors. So now if you're giving the same instruction to a whole bunch of these units that are doing multiplication and addition, you can amortize all of that and save that. So you can have a lot more parallelism if you know that you're roughly doing the same operation with different data all over. And this is...
And these, sorry, just before I forget. So, and these processors had an idea of a matrix on which they're working on.
Yeah.
Compared to Intel, which was more about single cell addressability, or...
Yeah, so when we are writing like a regular procedural program, we don't know what the next instruction is going to access. So sometimes you get nice sequential reads when you're reading from an array, writing to an array, but a lot of times it's just a random access of memory.
Which is single cells in some sense. So the big shift was the fact that we were able to go after an M by N matrix. And fundamentally, the processor in the SIMD case understands a matrix on which it's working. And there's a clean understanding of the matrix, which you just give it 2 coordinates and it knows the rectangle in which it's working. Which was fundamental to compute and how computing architectures became different with RISC versus CISC, or at least with GPUs versus CPUs. So at some level, this was a big shift. And Intel probably kept going deeper and deeper and deeper into complex instruction set, and still accessing random access, of memory, just individual cells. But as you said, there could be some prefetching and locality and things like that. But there was no structure to the memory, right? You mentioned something about complex managers, simple managers, assembly line. Was there anything to be said about the way Ford built cars, before which there was obviously car companies, and yet they came and simplified the assembly line? You know, is there an analogy there?
Yeah, I think you can definitely draw some parallelism. It's like there's like a pipeline of work to be done, and since everybody knows what they need to do, it's a lot more efficient. Right? That like everybody, like a whole bunch of people are kind of getting the same instruction and just different pieces of car that they're working on versus different pieces of data that they're working on.
So they have tasks that are well defined and so on. Okay, so we went from the era of 2000s, gaming, matrix and graphics and computer vision. Now era 4, 2010s. Important, very important decade, 2010s. Say more about ImageNet and RNNs. RNNs and GPUs.
So actually, I think there's a parallel development happening on the machine learning side in like 90s and 80s and 90s that may be worth talking about, right? So this is the era where embedding became mainstream. This is the era where convolution neural networks became mainstream for doing image recognition tasks and things like that. So
you're talking about the 90s or the 2010s?
90s.
Okay.
So somewhere like late 80s, actually, somewhere in late 80s, for the first time, the latent semantic indexing paper comes out, which has nothing to do with neural networks and machine learning as such, but the idea that you can take a set of words in a document and treat them as vectors, and they meaningfully represent topicality of the document, and you can deduce these topics by simply taking these very large one-hot vectors representing words and turn them into dense vectors that represent topics. Was a completely new idea.
And in this, conceptually, we are saying we're trying to map the meaning of words into a vector space, into an n-dimensional space. And seeing if they're close enough. If they're close enough, then they're semantically close. And, you know, the idea of an embedding is to take everything to a vector. Like convert that to a vector in this meaning space, this n-dimensional semantic space. You brought this up because you were trying to draw something to 2010. So say more about, first of all, you introduced a new word called convolution network, neural network. So for the edification of the audience, say more about what CNNs even were trying to do.
So these are like two parallel tracks that eventually converge. But so there's the language processing side where the embeddings got invented, and then there's the
idea of convolution.
The idea of convolution neural networks for image recognition and computer vision kind of thing.
What does the word convolution mean?
Okay, so convolution is a mathematical function, or rather a way of combining two math functions. So the simplest example of convolution could be a weighted sum of a time series data. Right? So let's say that I'm getting some readings, let's say body temperature, and there's some noise in those readings. I want to eliminate those noise. The way I can do it, I know that body temperature doesn't change that fast. So I can do a weighted sum, local weighted sum of the temperatures in last 5 minutes and say this is a much more meaningful reading than the individual reading that I got. Right?
So there's a sliding window.
There's a sliding window. Right? So you could think of this as composition of two math functions. So one is the time series of readings, and the other one is a simple math function that is zero everywhere except between 0 and 5 minutes where it's 1. And so what I'm doing is that I take a point here, and then I slide this other function which is between 0 and 5 minutes is 1, and then do the pointwise multiplication and add it. So that's the mathematical operation of convolution. Now I can play with the shape instead of this being like this rectangular flat thing, which is 1 at between 0 and 5 minutes and not 1 everywhere else, and make it more smooth. Like I could have exponential averaging, in which case it's like a curve that slowly decays over time.
So you're taking two curves and trying to add them up in some sense.
Yeah, so you're taking one curve and sliding the other one at a given point and doing a weighted sum. And so that's the idea of convolution.
And why did it matter for neural networks?
So the idea of convolution was used for signal processing for a long time. So, like you're reading electromagnetic waves and trying to decipher what was the signal. You would do all kinds of convolution.
Compared to the noise.
So you do all kinds of convolution. Now, the same idea also applies in 2 dimensions. Right? So you have a set of pixels. Instead of having a set of intensities along the timeline, now you have 2 dimensions along which you can vary x coordinate, y coordinate, and there are different intensities of different colors that you're reading, right? Now, you could smooth an image by doing a convolution with a math function that looks like a rectangle. So 1 in a certain part of rectangle, 0 everywhere. So this rectangle, if it is very narrow, then it doesn't do anything to your image. But as you make it wide, it starts smoothing the image, so taking local pixel and averaging. Right? So that's one kind of convolution you can do on image, which will just give you a more smoother version of the pixel. You can do the opposite also, which is like it's one side is +1, and right adjacent to it, there's a set of -1s. So one rectangle of +1s and one rectangle of -1s that's left of it. Now, when you do convolution with this, it's essentially taking sum of pixels on this side and taking a difference with respect to pixels on the other side. So every time there is an edge of sorts along the y-axis, its intensity will be very high. But everywhere else, it will just kind of cancel out because the smooth value of pixels on this side and this side should be roughly the same.
So this was all being done to do edge recognition.
Yeah. So you can design this second function in convolution, which are called kernels, to do all kinds of things. You can do horizontal edges, you can do vertical edges, you can do diagonal edges. You could smooth a local area just to get the intensity. All these things can be done. And computer vision people were doing it by handcrafting these functions. And the idea of convolution neural net was that these functions can be learned using neural networks.
Got it. So you mentioned this about the 90s.
Yeah.
But let's hop to the 2010s now.
Yeah.
So ImageNet and RNNs. So we're going to introduce yet another neural network called RNNs, which are different than CNNs.
Yeah.
So explain to people as to why it mattered and why did ImageNet matter in the 2010s?
Yeah. So ImageNet was essentially a data set of images that were labeled. So like this is a cow, this is a dog, this is a bird kind of thing. And researchers at Stanford created this unprecedented scale of labeled images that didn't exist before. And it became one of the first well-known benchmarks where people went after and tried to show that my algorithm is better than your algorithm in actually predicting these labels. And this was critical to a lot of development that happened after. So this data set together was essentially ImageNet.
ImageNet, yeah. And RNNs versus CNNs,
Yeah. So the R in RNN stands for recursive, so recursive neural network. So you're familiar with the recursive functions that call themselves. Right? So there's a similar idea here where there's a neural net and the output of it comes back as an input. So in some ways, you're making copies of this neural net and the output is feeding into another copy of this neural net, and then the output of that is feeding into another. And you can think of it as like, if these are functions, this is composition of function after function recursively.
And why did it matter? Physically, why did it matter? Why would I take the output of this function and feed it back as an input?
Yeah. So this is what introduces memory in a network. So far, all the other networks we've talked about so far have no notion of memory. Inputs come in, and then output gets produced, and then another input comes in and another output gets produced, and it has no memory of what it did before. Right? But the moment you take the output and feed it back into the input, now some of what happened before is present in the input.
And is this relevant for natural language compared to other things?
Yeah, so it's relevant for almost anything where you can't provide all the input at the same time. So it's relevant for natural language because you have a long sequence of words and you cannot take the whole long sequence of words and feed it into a neural net. It can be relevant for very large images. So CNN would still treat the whole image as a single input and produce the output. But let's say that you had you had much bigger images and smaller networks, and you could still use the idea of recursion and slowly sequentially read different blocks of the image.
And at some level, you are trying to really map a problem in the real world to hardware and memory and all that. Is that the reason why I need to look at a window of data as opposed to the whole data?
So RNNs got popular because of processing language. Right? So now imagine if you have a very long body of text that you're trying to translate or understand, and you can maybe read 1 word at a time, maybe 10 words at a time, maybe even 1,000 words at a time, but like how do you process the whole book? Now some of those things are getting defined now, but that was the idea that like I'm going to read 1 word at a time or 1 sentence at a time, and yet I should be able to understand the
context,
the entire context in there.
So memory and context are somewhat interrelated.
Yeah.
Say more on that for people. Like the word context matters, and is this where RNNs became popular?
Yeah. So anytime, or even if you're, let's say you're dealing with time series data, right? Let's say you're looking at revenue of a company and you're trying to predict revenue in future, or you're looking at the rate of outbreak of a certain disease and you're trying to predict the future. You want to be able to consume everything that happened before, which in theory is infinite, right? So you need some representation of what happened in the past, and that
to predict the future.
Yeah, that in a way is your memory. That in a way is all the context you have at this point to predict the future. So that's where the idea of RNNs came from.
And maybe just a little deeper into recursive neural networks and why they were computationally hard to do things with, because and we talked about this notion of even recursive programming versus memoization, for example, and so on. Say more about what is it that recursive functions, for example, were doing. I mean, in some sense, they were doing depth first something, they were coming out, they were going in again, they were redoing the same thing without memorizing the fact that they've gone down that tree before and so on. And of course, dynamic programming came on after that. Because we're going to get to the Big Bang of 2017. Attention is all that matters. But I want to build a case for people as to why this thing was computationally hard. The RNNs were probably not going to scale until we had the 2017 paper.
So RNNs were a reasonably successful class of neural networks. A lot of innovation happened around it. A lot of early neural net based machine translation stuff happened with RNNs. One problem in particular that was happening with RNNs was that this problem is called the problem of vanishing and exploding gradients. And again, we're going to do hand wave around it, but think of it as instead of the feedback in RNN where the output goes to input, you open up the recursion in the sense that like now you have multiple copies of the same network, and then the output from here feeds into a copy of it along with the next sequence input, and it feeds into the copy of it, and so on and so forth. So now if a particular RNN has, let's say, 100 layers, by the time you've opened it up, let's say 10 times, and now you have 1,000 layers between the output of this one to the input of this one. Okay? And so when we are computing gradient, remember the chain rule where you multiply the partial derivatives along the way. So now you're taking 1,000 partial derivatives and multiplying them together to compute the gradient here. The longer this chain gets, the more the chances that one of these partial derivatives will be too high or too low. If it's too low, then you've gone down to 0. That means that everything else will be 0 and no learning can happen because all the gradients are 0. If it's too high, then the size of the gradient is so large that the moment you apply it, like everything is off from where it was, and so it just becomes unstable and it cannot converge. So the longer this chain gets, the harder for it to converge in a meaningful way. Either the gradients just vanish to 0, in which case you stop learning, or they explode to infinity, in which case it becomes unstable and it's not converging anywhere. And why does it matter? So imagine the passage of text that says George Bush was 43rd, or I forget, president of the United States. He was also governor of Texas. How do you understand meaning of he without connecting it to George Bush over here, which is several words apart? Right? So that means that when you're processing with neural net, these thousands of layers of neural net have to communicate to be able to say, oh, this George Bush thing should be remembered through 10 loops through this 100-layer neural net. And then over here, it should combine with he so that it produces the meaning of he, which is George Bush.
So basically, there's a bunch of global variables that we wanted to really have to remember across these different recursions and so on.
Yeah.
So what was the tweak? And I know we have to talk about the problem of RNNs first before we get to the solution.
Yeah. So the problem with RNNs was that they couldn't remember anything from too far, because everything had to go through this recurrence layer.
So there was no global memory in some sense, right?
Think of it like exponential averaging. Right? So when you have a time series data and you're doing exponential averaging, you essentially take the last value, multiply it by 0.9, take the current value, multiply by 0.1, and then you get an average that represents the past. But because of this 0.1, within 10 steps, you basically forget whatever happened before that. It's almost meaningless. So a similar kind of thing happening with RNN, where as time passes, you kind of forget whatever happened before. So if you needed context from before to be able to meaningfully resolve what's being said now, you couldn't do it if it was too far apart.
Got it. So a big problem of context, deeper context, bigger context in RNNs.
Yeah.
Does it relate to anything we learned from dynamic programming days? In terms of memory?
Yeah. I guess you could draw some analogy about like just remembering the right things from the past that can be reused.
And was there a data structure requirement there?
Again, I think if you stretch the analogy somewhere, it will fit, but I'm not able to connect these things.
Got it. Because, for me, as you said, there's ideas if they're very new ideas, they probably are natural.
Yeah.
They have to be hundreds of years. And in this case, I'm talking about 30, 40 years of computing, because you have to learn from what was going on in the 80s and the 90s with programming and how it applies to... So maybe at some point, and we'll have to go a little deeper into that. But let's take a little break. We'll come back soon. We have to get into 2017 and beyond. We'll also talk a little bit about Google Translate and NLP and embeddings as well, which was happening in 2015 era. So after ImageNet and RNNs, we get into a little bit of the mobile phone and how we were doing language translation as well. But that's after the break, so stay tuned.